Hi, I'm Ryan Marcus. I'm a PhD student. I work with Olga. Today we're going to talk about query operator embeddings, which is a way to use machine learning on the internals of database management systems. So the problem that we're trying to look at is applying machine learning to a thing called query execution plans. So let's imagine that you have a database management system and you're doing some stuff with it, and you've got 4 tables. You've got one table with your students that has your student ID numbers and your student names. You have another table called enrolled, which maps student ID numbers to the course ID that a student is enrolled in. You have a table called professor, which maps professor IDs to professor names. And you have a table called teaches, which tells you which professors teach which courses. A natural question you might want to ask about this data is how many students does each professor teach? If you're familiar with SQL, here's the giant mess that you would use in order to get that out. The problem is with query optimization is that there are many ways to compute the answer to this query. So for example, one way to compute the answer to this query would be to take the student table and the enrolled table and create a list of all the student names to the course IDs that they're in. Then separately, combine the list of professor names with the teaches relation to figure out what professor teaches what course, then combine those all together, then group them using a hash operator to do the count. However, we also could have done this grouping operation via sorting. Additionally, we didn't have to do the joins in this particular order. We could have joined the joins in this order. Started with student and enrolled, then merged in teaches, then merged in professor, then did a group by sort. Or we could have done it in a completely different way, started with professor, then does teaches, then enrolled, then students. You can prove nicely and mathematically that these things scale with something called the Catalan numbers, which means they are very exponential, very, very large, very, very fast. So we want to be able to do something to analyze this space. So we want to be able to ask questions like, how long will this particular operator take? Is it going to take too long? Is it going to take 5 hours and my user is going to walk away? Is this operator going to use too much RAM? If my system only has 4 gigs, is this particular join going to require 8 gigs of RAM? Or is it a malicious operator? Is this an operator that an outside person injected into my system to try to steal data from me or something like that? And so the way that we want to do this, because it's 2019, means that we have to use machine learning in order to do it. But the problem with using, so the trend of replacing or augmenting database management system components with machine learning has been long running, and it's been going on for a very long time now. There's been recently papers at CIDR and Sigma talking about how to do join order enumeration, how to estimate the cardinalities of large join queries, how to do dynamic query admission, and even how to do query scheduling, all with machine learning. However, all of these awesome new approaches all have one common problem, which is featurization. So the way that this actually comes about and gets actualized in the real world is that there's one particular lab out there at some university, and they identify a task. They're like, okay, we want to predict if a query operator is going to take more than 5 minutes to run or not. Then they gather a data set represented by these little queues here, and then they come up with features. They look at that data set and they think, what piece of information is useful about my queries that might help me predict my answer? So they put all that stuff together into something called a featurizer. So the queries go into the featurizer and out come vectors. Then we use those vectors, we do the standard thing, we train models, we do cross-validation, we write papers, we get rejections, etc., right? The problem is that how this actually happens is that every single lab identifies different tasks and comes up with different featurizations. And the featurizing a query is not a trivial amount of work, right? You have to examine it, you have to figure out what might be relevant, you have to gather certain statistics. It's a lot of effort. So the goal of this project is to replace that featurization bar with a single common pattern that's going to be useful for a multitude of tasks. So regardless of the task that you want to do with a particular query operator, we want to find a way to come up with a featurization of those particular operators that will be helpful for your task. So with that background information, for this talk, instead of focusing at the query level, we're going to focus at the operator level. So we're going to look at how to turn one particular operator, like a join or a group by, into a vector. And ideally, we want those vectors to be usable by off-the-shelf machine learning algorithms like random forest or support vector machines. We're going to talk about why it's hard. We're going to talk about how we can just straight up lift a technique from natural language processing to solve this problem for us. And then we're going to show some experimental results. So the big problem, the reason this is difficult is because of sparsity. If I have a join operator, I can easily featurize that join operator with a large number of pieces of information, right? I can look at the join operator and figure out, oh, there's an algorithm. Is it a hash join or a merge join? I can see selectivity information. I know approximately how many rows there's going to be in it. I might know the hash algorithm that's used, etc. So I can very easily take all of these things and throw them into a vector. Right, so we can use one-hot encoding. If we have 3 different types of joins, we can use 3 different entries in a vector and put a 1 in the type that we're using. The problem is I also have other types of operators. For example, a selection operator. The selection operator has a different chunk of information. So if I want to do machine learning on query operators, I need one featureization that will work for both of these things. So the easiest thing to do is to just glue them together, right? We use the first entries for the join features and the bottom entries for the select features, and then the others get set to 0. The problem with this representation, of course, is that it becomes very, very sparse very, very quickly. The problem with sparse vectors is that they have they impact machine learning algorithms in a really negative way. A lot of machine learning algorithms can't handle them. I'm not going to go into huge details, but the short of it is that very sparse data is a very big problem, and we need to find a way to fix that. So the natural language processing community has been dealing with this problem for an extremely long time, right? If you think of words inside of a sentence, how do you encode that word? Well, just the letters that are involved in the word don't really matter, right? Because there's plenty of words where I can rearrange the letters and get completely different meanings. But one approach that's very easy is to use a one-hot word vector. In other words, you count out how many total words you have, the size of your vocabulary, and then you assign each particular word to an index. So for example, for the word east, I can create a vector where each position in that vector is assigned a particular word. I go to the east one and I make it a 1. Boom, now I have a one-hot vector. So I've successfully vectorized a word. However, this vectored representation is very, very, very not useful, right? It's very hard to work with. It doesn't contain a lot of information. What we really want is dense vectors, where every dimension of the vector tells us something interesting about the problem, and where the distances between vectors are somewhat relevant. So how can we go from sparse vectors to these dense vectors? If we want to get out a lower dimensional dense vector space with some kind of semantic meaning, like for example the words king and queen should be closer to each other than the word bananas and headphones, we need some way to do that. And the solution from the natural language processing community is the idea of a neural embedding. So the intuition behind a neural embedding is that different words appear in different contexts. For example, in the sentence, blank is a tasty fruit, I would expect the word apple and banana, whereas in the sentence, long live the blank, I would expect the word queen or king, and not the converse, right? Long live the apple is not a sentence that you're likely to hear. So how can we take advantage of this contextual information in order to create vectors? And again, the natural language processing community has an answer. There's a bunch of different ways to do this. They're called things like bag of words or skipgram, but the basic idea is that you take a large unlabeled corpus of data, so like a whole bunch of sentences. So for example, the sentence, the quick brown fox jumped over the lazy dog, and you train this neural network to do a particular task. You train it to take in the one hot encoded vector of a particular word, say brown, run it through a neural network with a particular structure, and then predict the context of that particular word. So in my example here, I'm showing predicting the neighboring words, which in this case are quick and fox. So one important thing to note, to note about this embedding structure is that the neural network is given a very particular shape. We have kind of a big part in the middle, and then we have a very narrow layer, and then we have our prediction layers afterwards. This middle part can be thought of as a learned embedding, because by forcing this middle part to be small, we create something called an information bottleneck, which forces the neural network to learn a representation inside of that layer that is useful for predicting the context of the query. So this gives us what we want, more or less, for words, which is distilled dense vectors with semantic meaning. So the overall view, 100-level view of the approach is that you have some one-hot sparse vectors. You want to turn them into dense vectors. So you take your sentence, the quick brown fox jumped over the lazy dog, and you trained a neural network to map quick to the unbrown, brown to quick and fox, etc. The results from the NLP community about this are really awesome. The words apple and banana end up having similar vectors because we see them in similar contexts. And the words like oligarch and doorknob have very dissimilar vectors because you almost never see them in the same context. And additionally, these dense vectors work very well as inputs to stock machine learning algorithms, even things like linear models, logistic regression, etc. So this is great, but we don't have sentences. What we have are trees of operators. So how can we embed each one of these physical operators inside of our execution plan? Well, we need a notion of context, and in a query execution plan, it's sort of obviously the children of a particular operator, right? For example, if I'm the merge join over there, my two children are an index scan. And the intuition here that is similar to the intuition for words, right? Like in the sentence, blank is a tasty fruit, we expect apple or banana, but not king or queen. Here, if my particular operator is something that's doing an average, then I'm going to expect my child not to be something like phone number, right? Because the average of phone numbers is meaningless. Or if I'm a max operator, I'm going to expect my input not to be social security numbers, because the maximum social security numbers is a meaningless concept, right? Similarly, you can think of things like if it's the distance between two things, it's probably not names, right? Like I normally don't care about the vectorized distance between two people's last names. So there's a lot of contextual information that's embedded inside of this tree that we're going to try to take advantage of. So just like in the natural language processing community, where we took our sentence and we inputted quick and tried to guess the and Brown, Brown and tried to guess quick and Fox, Fox and tried to guess the other two, you get the idea. We're going to take our neural network, and when we're given this merge join, a nested loop join operator at the top, we're going to try to guess this filter in this merge join. If there's just one child, then we're only going to try to predict that single child. So for this filter, we predict a table scan. And then for our leaf nodes, we're going to just try to guess the empty vector null, because they don't have any particular children. So in order to evaluate this approach, we took a big old standard problem in the database community called TPC-DS. We created a 1 terabyte database of it. We took an off-the-shelf commercial database system. We executed and recorded about 20,000 queries, which took about 3 weeks. That data set comprises about 1 million operators, and then we trained an embedding network to do this guess the children approach. So the input vectors, the one-hot vectors, or the size of a vocabulary, so to speak, was 384 elements, and our embedded dimension was about 32 elements. So that narrow layer in the neural network was about 32. So in order to evaluate these, I hope you all brought your 32-dimensional glasses, because it's really hard to visualize those space. So what we did instead was we used a technique called T-Sne, which is basically a way to project a high-dimensional space down into a low-dimensional space for visualization. What it tries to do is it tries to make sure that things that are close together in the high-dimensional space stay close together in the low-dimensional space, and then project those to you. So here they are. Woohoo. So note that the x and y axis here is completely meaningless. These are just the numbers that T-Sne came up with. And all of these little dots recommend are query operators. So this plot on its own obviously is not very useful. But for my first trick, we're going to color each one of these query operators based on whether or not they use too much memory. So when we do that, what we see is two very distinct and defined clusters, right? One on the left here and one on the right. This means that the contextual information that we got from the unsupervised model training, right, just looking at the query plan, is actually creating features that are useful for predicting whether or not a particular operator is going to use too much memory. So this is a really good sign, right? Because if they're clustered together in this low-dimensional space, then our machine learning algorithms that are good at learning linearly separable boundaries should be able to do a good job of looking at it, right? But it's not just the joins that use too much memory. We can also look at cardinality estimation. So a cardinality estimate, for those of you who aren't aware, is when the database's optimizer looks at a particular join and tries to guess, okay, is this how many rows is this join going to produce? It's a very hard problem, especially as you get up the tree. But here we can look at, for this particular commercial database system, where they overpredicted, underpredicted, and where they got it about right. And indeed, we see a lot of natural clusters forming in the data, right? This means that there's some kind of systemic bias to the cardinality estimator's model, right? Like if there's contextual information that is causing you to systematically under or overestimate, that probably means you have a bug somewhere, right? Or that it's a very hard problem. We can also additionally look at how long each operator takes to actually run. So here the cool colors represent really fast operators and the hot colors represent really, really slow operators. And again, we see a lot of natural clusters forming, you know, a bunch of blue stuff over here and like a bunch of hotter colors over here. So again, this is a great sign that a machine learning algorithm is going to be able to predict these things. But the proof is in the pudding. So the next thing we did for our experimental evaluation was we trained a whole bunch of off-the-shelf machine learning models against these embeddings, and we tried to do a bunch of particular tasks. I'm only going to talk about 2 of them today. The first is detecting spill joins, which corresponds to the plot you saw 2 times ago. We're trying to predict whether or not a join will use too much memory. And the second is operator admission control. If one operator in a query plan is going to take more than 5 minutes to run, the whole query plan is probably going to be pretty nasty. And maybe you want to ask the user to confirm, like, hey, do you really want me to spend 6 hours computing this? We have some additional applications listed in the paper that you can look up if you want, and we did the standard cross-validation techniques. For spill join detection, we have a prior of like 82%, meaning that 82% of the spill joins don't spill. So if you were to just guess it's not going to spill, you'd get 82% accuracy. We trained a whole bunch of models using both the sparse embeddings that we used as input to our neural network and with the embedded vectors that were outputted. And as you can see, we get quite the nice bump when we use those embedded outputs. And in fact, the models trained on the sparse vectors are barely able to beat the prior baseline. And in the case of logistic regression, it actually just learns a bias term. All the other terms are 0. So this is a great sign that the contextual information that we get from the operators is useful for predicting this very useful semantic property. operator emission control, so this is trying to guess if a particular operator is going to use too much memory or not. Very similar results, right? We see a bit more improvements from the prior this time, but again, using the embedded networks, again, proves that context matters, right? That when we know the context of a particular operator, it's much easier to guess whether or not that operator is going to use a lot of time or not. So, take nothing away from this talk. Remember that you should use context as much as you can in machine learning. Take advantage of the natural asymmetry between the huge amount of unlabeled data we have and the small amount of labeled data that you have for your actual problem. Do something to take advantage of the structures and natural patterns that appear in those big data sets, because those will create natural features that you can use for a variety of tasks when you actually have to go and label data. That's all I've got. You can find me on the internet. Thanks. Questions? This thing has a mode where it's supposed to record the whole room, but I don't know if it works. We'll find out. Yeah. Yes.
Can your tree ever be a graph where a node at some point in the tree can have like multiple parents?
So it depends on the database system. So with systems like Oracle and SQL Server and Postgres, generally no. Generally you do have a strict tree property. But with systems like Spark SQL and other systems, you can have more of a DAG kind of setup. You're guaranteed not to have cycles, obviously, but otherwise those techniques kind of become much more difficult. We talk a little bit in the paper about how there's this much more complex idea called a graph embedding that you can use to sort of capture features and patterns that appear in those, but it's like a bit more involved. Yeah.
And as for the dimensions for embedding, I'm sure you've experimented with some other numbers other than 32, but did 32 give you the best performance?
So we're actually not entirely sure how we're supposed to evaluate. So we tested 64, 32, 16, 8, and 4. And we found that 64 and 32 were about the same. And then there was a huge drop when we went down to 16, and then another huge drop when we went down to 8. And so I don't know if there's standard techniques for evaluating what the right embedding size is, but we looked at that chart and went, okay, well, 32 is smaller than 64, and the performance is about the same, so we'll go with 32. Yeah, I don't know if anybody knows. I know a lot of you are linguists, if you happen to know what the right way of picking an embedding size is. But
because I've seen embedding size go up to 300.
Right, yeah. I think when because like our vocabulary, right, our input vectors are only like 400 elements or so. So if we were to do an embedding size of like 300, it'd be like, okay. But yeah, I think like the Google word vex, right, like some of those are huge, right? Yeah. But I guess there's not as much like diversity in query plans as there is in natural language.